All right, cool. One last lecture before Friday we'll take the day off and then come back after Thanksgiving break for working on Module 5 work. Sound like a plan? It's Friday afternoon, right before the only break of fall semester. I think it's time to just call it, right? So last time we were taking a look at project 4. So I'll just start off with like logistics kind of stuff. Our goal is wrap up project number 4 today, and then project 5, like some kind of work in progress. So make sure you have a plan so that when we meet after the break, we can get into details of like, what does your free body diagram look like? How many degrees of freedom you're dealing with? Like, how are you applying methods that we're using in class to some kind of personal project, personal or could be other classes. Like if you didn't like get into the dynamics of something in a different class, you could look at like how that works here. Or it could be like a hobby kind of project of like, I've never really thought about how this thing works. Let me try to reverse engineer and see how motion and forces all get to the thing that I'm trying to look at. So that's Friday. Turn in like project 5 plan. It can be rough, like it could be a note card. We've done that for all of the quizzes that we build. It's like a note card of like, what concepts am I trying to cover? What's my general sort of problem? What forces are involved? That's enough for like Friday. Cool. All right. Yeah.
So this project 4 did?
That one.
SECT says like 5 days ago.
5 days ago? Are you sure? That can't be right. It was supposed to, I could have sworn I changed it. Oh my God. Let's look at month. Project 3, what is this? October, November. Why is it last week? I wanted it here. Like, I swear I changed this. Is it already done? Do you have questions on revising it? I wanted it due like tomorrow. That's what I wanted, but Husky CT said last week. Thanks. Have you already finished it? Like, is it turned in, done? Done? All right, so let's say like kernel run all. Just make all the graphs. So why does it start spinning backwards if your chord is too long? Yeah.
Isn't it just because of the model that you're using? Like the equation that you had in the code?
Yep.
A minus, it's like a positive term, and minus the term that depends on t is negative.
Okay.
So the longer the t is to a certain point, it's getting a negative.
Okay. But that's in there, like the code that's in here is is just physics. So are you saying up? Which part are you saying? WB? This one?
Yes.
Okay. I mean, that's like, it's just taking a physics formula and plugging it into Python code. So even if it wasn't, but why is there negatives? Like, I mean, it makes sense that it should be, the goal is reduce that rotation rate. So it does make sense that it shouldn't add rotation. That would be a bad yo-yo de-spinning mechanism.
Could you ever, by like adding yo-yos, could you ever make the rotation negative? Because the torque that the yo-yos are adding, wouldn't it go to zero the second that it's not spinning?
No, the yo-yo, so here, if we come back up to like this thing, as these things, and like some of the videos, if you watch videos, like usually the spacecraft is spinning one direction, they activate yo-yo, and then by the end it's spinning in the opposite direction. Like, it does create a negative rotation rate. The goal is zero. You're not going to hit exactly zero, but you get it pretty slow. And so kind of physically what's happening is once the yo-yos like start acting and the cords are increasing length, kind of unspooling, there's nothing slowing them down. They'll continue rotating if you were moving at 100 hertz, like 100 rotations per second, they continue moving at 100 cycles per second around your spacecraft, and the tension is not slowing that down at all. So they keep spinning they keep same speed, meanwhile your spacecraft is going slower, and then at some point it starts going the opposite direction. So one answer could just be math says that it's got to be negative, because as time continues, a negative t will soon enough be a negative omega, like theta dot sort of thing. Yeah.
And eventually, if it was not released, it's
Are you saying like it ravels back up, or?
or just make the shit follow its own.
Okay. Within that,
By the way, the same right now.
so yo-yos are, they say they're
It
like,
shifts from the positive,
yeah.
the positive spin, the other's like negative spin.
Oh, why are the yo-yos negative? Yeah. Okay. Yeah.
That's like what was going on in my head.
Okay. Yeah.
Mine crashed like 3 times. I'm trying to get rid
Yeah.
Does that have something to do with potential?
Is there a difference in potential energy anywhere here?
It's conservative.
Okay.
Yeah, it's true. And then people crash it. So get that.
So maybe it's gravity, because it's accurate.
This one.
No, I guess because it's.
This is like a deep space sort of problem.
Right.
I mean, we could say there's gravity, but it would
Yeah.
change like the angles. Okay.
That took me so long to figure out.
Yeah.
No. Yeah.
I was dead wrong. I thought that it was only because of the model. I thought the second it stopped spinning. Yo-yos are causing drag. I know we're in space, but I feel like once it stops spinning, they would be perpendicular to the as an intent. Yeah, in my head, I feel like that would stop spinning and cause it to.
Well, like, if you're in space and you like cast out fishing.
So it's just the fact that it's, yeah, so it's just the fact that it's causing it has like a negative.
Oh, there's that.
So negative. Yeah, it makes sense because
I knew there was another.
I guess that force that they applied is just keep it spinning in the other direction.
Okay.
But yeah, in my head, I wanted to stop applying this force the second it stops.
Yeah. Okay. But then you'll do it like, I think we should like,
Yeah, I was waiting in line this morning. So my friend.
Yeah.
over like me.
Yeah, exactly.
Yeah, 10 something. Yeah.
That's gonna be really fun, honestly.
Even after that.
Yeah,
But it,
yeah, no, that,
yeah, but
it's
the,
gonna be worth it because. Yeah.
Yeah.
I think.
Yeah.
I just think so. But I guess. Yeah, I figured they were just there. No, it's more complicated. I just. Two pieces more stiff. Get the bag. Yeah, it's not like one person. Exactly. Which is. Yeah,
I didn't see that. This comes from the bottom. I used to do that in this room before. Look, just control
so you're just gonna take this together.
it.
All right, so I'm kind of drawing up here, like the progression of very simplified, but not a great drawing, but progression of my like cylinder flying out into space. Initially, yo-yos and my payload, like the main thing that I'm trying to de-spin. It's all spinning together. And then I release it, and then at some point I stop moving, but the yo-yos, there's nothing stopping them from moving. The yo-yos are the stopping motion. That's the only thing. All we did was release them. Yeah. Kind of get it? Okay, what do you?
Okay, so the yo-yo spin, previous spin counterclockwise.
In this case, we have like everything. We'll say yo-yo like that, and we'll say so I'm just drawing like a couple like arrows, bigger arrow, more rotation, smaller arrow, less rotation. And then in the last one, we have a negative. Yo-yos are still, I guess if I'm just talking about spin, like yo-yos haven't really changed, right? Because there's a tension causing them to move in some kind of circle, like not quite a circle, but a path, changing their path, but it's always normal to the path, the tension. So we start off, everything's moving same speed. We release yo-yos. At some point, our payload is basically not rotating at all. Yo-yos, nothing changed it, so they're still same rotation. And if we hang on to them, just kind of over design, say like, all right, make the length we wanted was six meters, so let's throw 12 in there just to be safe. Now we're spinning backwards. So our payload was this way, now it's corkscrewing the other way. So what happened? Did anybody talk? Did anybody like hear something? It all clicked. There's two ways we can kind of go about this. One is sort of like stick to Newton's laws, and F is ma, and it works. Go like. The tension's always pointing at those yo-yos, and we're not changing the direction of that tension.
So it's like would be at this causes spin counterclockwise.
Yeah, so we're creating a torque, and that torque is always against our initial motion. And if we hold on to that string, we didn't get rid of the torque, it's still there. So instead of thinking this is like a brake brings you to a stop. This is more like
brake stop rotation. This is applying the force in the opposite direction.
Yeah.
Slow down.
Yeah. So
I guess we'll take it 0. It starts spinning opposite direction.
Yeah. So this is one way to think about it. Is like we have a torque And if we don't let go of that string, then the torque is still applied. It's changing. Like it's not that the torque is a constant thing, but it's always in one direction. It's always opposite to that first motion. So that's one. Same thing is like if have you ever driven a boat? You go to brake. The boats don't have brakes. They have a reverse. Put it in reverse. You can't stop the boat with reverse. I mean, you can bring it to a stop, but if you keep it in reverse of like, let me really bring it to a stop, now you're just moving backwards. Similar idea here. It's just we're torquing it instead of pushing on it. Or we use our new friend of angular momentum. Is there any torque on the combination of the yo-yos and our payload?
Well, I think so.
The torque, yeah? So we say didn't draw well. So what are, doesn't look right. What forces are acting on the system as a whole? There's no gravity, at least no like noticeable gravity. We're in like microgravity sort of idea. Is there drag?
No, in space.
We're in space, okay, no drag. Spring forces? Springs? No? Electromagnetic interactions? Maybe, but probably not big enough. Okay.
Yeah, I don't think there are any external forces acting on this.
Not as a whole, right? Like as a whole, there's no external force acting on our system. The only thing we're doing is like we're redistributing mass. We're moving mass away. And all the tension forces are all internal to this free body diagram. So sum of the moments is 0. So angular momentum has to be constant. So initially we have H is this. Keep losing my pen for some reason. So initially, like our yo-yos don't have a lot of momentum, but our payload does. And then H is maybe like a bigger, and meanwhile this one's smaller. Put P and Y. And then finally at the end, yo-yos are big, and payload has to be negative because it still has to be the same vector. Like it's still gotta have the same magnitude, same direction, because we're not creating any external torque on the system. How does that one feel? Yeah, we have to have whatever we started with for angular momentum. It's got to be the same from beginning to end. What are the things you noticed here? I guess this is kind of like 2 steps, right? What did you notice about your design? And then also, I mean, the question, we kind of looked at this at least for one example, but for your payload, what was happening as mass of the yo-yos is changing, or what else did you notice? Was there anything worth exploring, talking about? Oh, it spreads out, like it takes longer and more. Yeah. Yeah, that is cool. So how would you describe like that change? Like sharp to not sharp, I guess. What was changing there? Yeah, okay. Yeah, that makes sense to me. It's like heavier is more effective, and so yeah, happens sooner. If you were putting it on your spaceship, would you want a heavy one or a light one? Which one would be better? But it takes longer. Yeah. To avoid, yeah. Or let them work back up, straight down. Yeah. Yeah. Anything you noticed in the design? Yeah, changing things. Yeah. Okay. Yeah.
The paths of the challenge. Pretty sure this is still the same. I actually changed that now. It's closer. So it's more than 5 here.
Okay.
Yep. Those two things I changed. This max.
Okay.
Those are the things I have.
Yeah. Nice. So there's a couple of ways. Some people were noticing, like this time is changing, or path, like how those are changing, like direction that the yo-yos leave. The payload is different. Like if I'm trying to report like, okay, fellow engineers, I'm designing this yo-yo D-spin, and I want to give like a few examples of how much cord we need, how big this mass should be. One way to do that is just kind of keep track, like make a table of how much mass did you have, what was the cord length, how much time did it take. So we'll say mass, length, time. I guess I should add some units, right? Oh yeah, let's make it markdown. And you don't have to use markdown if you don't want. You can use any kind of table. So in this case, I have mass of 30 grams. It took 9.21 and 0.07 seconds. And then if I double that, too far, go up to 0.06 and just run through. Now I've got 60 grams, 7.75 meters, and 0.06 seconds. And I could do this like a few times to kind of detail, hey look, increasing mass decreases size of cord, and it's also decreasing how long this thing takes to act. But there was also a great observation of like the slope going through that 0 point is getting shallower. The bigger the mass, the steeper the curve. So let's do an extreme, make it not too extreme. We'll just say, change it down to like 1 gram. And we can see it took longer, but it's also shallower. So the slope is getting smaller as we go through that. Sometimes that's a good thing because that means that there's less variability. Because like whether it took 0.15 or 0.16, slope was pretty shallow, so it should be about right. Same thing for the length of the cord. So you might want a smaller mass for 2 reasons. One, it's smaller, and the sensitivity. So that one way to call that is the sensitivity. Like the slope of the curve gets steeper the heavier the mass is, so we want a less sensitive braking mechanism. And we'll add another row down here since we did more work. 1 gram, 21.56, 0.15 seconds. And here we can kind of see time is almost like for 30 times more mass, it doubled the time, rather than, it wasn't 30 times longer, it was just 2 times. But anyway, practice. So I wanted to show like practicing how to like detail a quantified answer. Like take what you're seeing and try to put some numbers to it. messing around with stuff. Variables. No, it's all exactly what you expected.
I mean, for the Earth to slow down, I use the massive moons.
Okay. Yeah.
And then, no, it's like pretty similar with everything else. Like the release points are pretty low.
Okay.
And the cord is long, obviously, those are really big masses. It's like
Yeah.
13 megawatts or meters, and I'm pretty sure it's like 30 billion meters.
Okay. Yeah.
I don't know meters.
Yeah. Yeah. How many
It could happen.
radii is that? Or diameters?
Yeah. The diameter. 12. So it's 2 diameters.
2 diameters. That's it. Yeah.
Yes.
Just that entire cord.
Yeah.
So it. Yeah, and there we are. Like we're not accounting for the fact that the Earth and the Moon do have.
So there's nothing.
Yeah, there's no gravity. There's nothing.
Nothing.
Yeah. Anything else?
Is it fair to say, like, that a pattern memories is how this converges? You're at the same negative value, is that kind of just kicking because of the.
Oh, yeah, what is it converging to?
It's converging to the negative version of this value,
Okay.
which tells me that's just modeling.
Is that
the conservation
always,
thing.
is that always true?
Yeah, I've played with around
Really?
versions for that.
Okay.
Yeah.
Yeah.
I mean, unless I have a John Ziegler from I've
Yeah,
played with a
yeah.
lot of different payloads and masses, and it always
Okay.
produces the same pattern.
Alright.
It's really cool.
Yeah, we talked about turns negative, but we didn't really count.
Right.
Yeah.
I can be really.
All right, so here's a question coming back to like positive, negative spin. How come someone noticed that there's like an asymptote of this function and the horizontal, like it's always trying to approach the negative value of wherever you started. So here I started 150 radians per second, and if I build a cord long enough, I'm gonna spin it backwards at 150 radians per second. And I can change time, I could change like how long, or I could change how fast. I can change mass. 0.02, and we'll change this, make it 20. And we still, we need more time, huh? We're still hitting that like negative 20. So we start at 20, and if we just hold on to it as long as we can, we're gonna end up at negative 20.
Like, so that's in 3 seconds.
Yeah, after like 3-4 seconds, we're right there at like spinning same speed but opposite direction. Oh, what? Yeah, like why does it not? Why doesn't it just keep decreasing? Because if we think about it from a from like Newton's laws, there's always a tension. Shouldn't it just keep accelerating? If you have tension, there's always a torque. Even if the torque is small, it'll just keep slowly ratcheting it up in that direction. Yeah. But great, thanks for bringing that up. That's a great observation about like, it seems to be a constant that you can only reverse the spin so much, and then at some point you're just back to where you started, but
But the opposite way.
opposite way. Yeah.
I like those concerns, got pretty, completely opposite versus.
Yeah. Yeah.
So, yeah.
Sorry. Oh, okay. Sorry. How did the project go overall? Yeah, payload. Did you notice anything in the design work? Did you really playing around with very
Backbone, German here.
Yeah.
I don't do that.
Okay.
Plus two searches.
Did you notice anything else that you're working through? Or are you doing?
Well, I.
Okay.
The league one's about the
I was
last.
just thinking about how.
What's the website?
Oh, okay, yeah. Oh. Yeah. I didn't do a sensitivity of like how people they operate. Yes, naturally not. But I wonder how closely slightly shift center of mass towards one or the other. And something like that. Okay, there you go. Yeah. Oh, yeah. Nice. Did you get there? Yeah. Right. Right. So we'll just find it. Going pretty good design. Okay. Yeah.
Well, I mean, it's like, I mean, if I want to get on
Yeah.
so this is.
Oh, okay. Yeah.
Also,
Yeah. Yeah.
given that dark options we were.
Okay.
Now we're trying to optimize what we need to
Yeah. Yes. Yeah. I mean, really, I hear we're saying cable is massless, which is that's a good assumption. But in reality, cable is not massless. Coil, 100 meter steel cable. Definitely, cable is a very significant versus 90 meters. Even that. So you could have a term, whatever length of cable, whatever gauge has certain mass per length. Multiply that and say, when you try to line the general, your mass plus cable mass. Yeah. Yeah. Do you notice anything as you're going through design learning?
Yeah.
Okay. For this project, okay. So what happened is, what was like
It's like, yeah, like
why do they, so what do you mean?
I'm gonna need to go back.
Okay, yeah.
I'll come back to you.
That's mostly what it's going to do.
Yeah, it's like, things are baked in, the analysis that we have.
That should be.
If there's a year, it's
Makes sense.
All right, have a great break.